Welcome to the Crazy Hat Chemist. So here we go with another video. Today's video is on chemical reactions worksheet number 3. And before you watch this video, I'm going to assume that you have watched my types of chemical reactions video. That gives the foundation of this. In addition to that, chemical reactions worksheet number 1 and 2. And then here we go, number 3. So what are we trying to do here for number 3? So the key feature here on number 3 is that we have reactants and products written out after having determined the type of reaction and then from that type of reaction determining the products. Now what we're going to do is we're going to balance each chemical reaction using what are called stoichiometric coefficients. Those are whole numbers in front of formulas. So that is our goal here today, is to write stoichiometric coefficients by balancing each equation. So I'm going to give you some simple do's and do nots, and hopefully that will help with your journey here in balancing chemical reactions. So number 1, you cannot end with fractional coefficients. As you cruise on through later on in chemistry, that will change and fractional coefficients will be okay. But for at this moment in time, the answer is no, you cannot use fractional coefficients. Furthermore, try not to do something that is taught in middle school. And I'm going to show you an example of that. And this is completely inefficient. Don't do this. You can actually do this in your head if you are following along on this video. So what we're going to do is we're going to zoom in on these problems a little bit more, and that will get us to where we need to be, where it's very large. All right, so let's do that right now. Okay, so right now we're zoomed on in, and here is a do not. So let's not do this, and that is the following. We're going to write down a zinc, and then we're going to write a hydrogen and a chlorine on one side, a zinc, a hydrogen, and a chlorine on the other side. And then let's start counting them. Let's say there's one zinc on the reactant side, one zinc on the product side. So I'm going to write a 1 and a 1. There's one hydrogen on the reactant side and two hydrogens on the product side. And there's one chlorine on the reactant side and two chlorines on the product side. This method will take you forever. So you know what? You're going to take this and you're going to say, nope, the Crazy Hat Chemist says, don't do it this way. Throw it away, crumple it up and throw it away. There it goes, right in the garbage, folks. Okay, this is what you're going to do. Okay. What you are going to do is you're going to say how many of each element are on the reactant and product side. So what we're going to start off with is say how many zincs are on the reactant side? 1. How many zincs are on the product side? 1. So that's all I need to look at this moment in time. Now I'm going to go for the next element. The next element is hydrogen. How many hydrogens on the reactant side? 1. How many on the product side? 2. Therefore, I need to place a stoichiometric coefficient, and those stoichiometric coefficients can go right where my red lines are. That would be whole numbers. So if there's 1 hydrogen on the reactant side, 2 on the product side, and I'll highlight that 2 just so that you understand where that is coming from. So there's that 2 right there. So there's 1 hydrogen here on the reactant side, 2 hydrogens on the product side, and I'm going to place this 2 here. That 2 is 2 times 1 hydrogen. That's 2 hydrogens on the reactant side and 2 on the product side. So the hydrogens are now balanced. Then I have 2 times 1, that's 2 chlorines on the reactant side, and then 2 chlorines on the product side. Fantastic. Perfect. I'm actually done. So the other thing that we want to do is we want to understand that this arrow, we're going to leave that arrow there, but we're going to imagine it as an equal sign. So what we are trying to do here today is writing stoichiometric coefficients, and that will allow us to have an equal number of each element on each side. This side, on the left-hand side of the arrow, are the reactants. These on the right-hand side of the arrow are the products. So we want an equal number of each element on the reactant and product side. Furthermore, if there is no number in front of that, like on the zinc, it's actually assumed to be a 1. So you can put them there if you want to, but they don't necessarily need to belong there written down because they are assumed if they are not on there. So that's why I put those in pencil for you so that you understand that you don't actually have to put those ones there. They are assumed if there's no number. All right. So let's move on to the second problem. I'm going to underline here where stoichiometric coefficients will be or should be. So the other thing that we're going to do now that we're moving on to the next problem, the next little piece of advice is that what you're going to do is you are going to use the most complicated formula first, and that's where you're going to start. So the most complicated formula is the formula with the most unusual number of elements and the most number of those unusual number of elements. So for example, I would start here with this calcium hydroxide. There's one calcium, one on the reactant side, one on the product side. They're balanced. This too distributes because a parentheses is very similar to like a parentheses in your math class, right? So if we were to do like a math problem, if we have a 2 parentheses a 3x plus y, what you do is you distribute this 2 over both the terms inside the parentheses. So that actually is 6x plus 2y is your answer here. So we are going to be doing the same thing with this 2. This 2 is distributed with the hydrogen. So now there are 2 hydrogens, and with the oxygen. So there are 2 oxygens as well as hydrogens. It's very similar to having this stoichiometric 2. It distributes across everything that's in that formula and but nothing beyond that. That means that there are 2 hydrogens and 2 chlorines given that stoichiometric 2. There's 1 zinc and 1 times 2, that's 2 chlorines. Okay, so we're going to slide this back on over here just like that. And now what we're going to do is we're going to go, aha, there's 1 calcium, 1 calcium. There are 2 oxygens on the reactant side with that subscript. Then there's 1 oxygen here. So that means I'm going to place a 2 right here like that. That will give me 2 oxygens. Then how many hydrogens on the reaction side? 2 times 1, that's 2. Plus 1, that's a total of 3. Okay, over here, there are 2 times 1 plus 2 times 1. That's 2 plus 2, that's 4 hydrogens. Over here, so on the product side, I have 4. On the reactant side, I have actually 3. That might be a little bit more difficult to deal with, so we're going to do something else instead. And that is how many chlorines, an unusual element, 1 chlorine on the reactant side and 2 chlorines on the product side. So I'm going to place a 2 right here in front of the hydrochloric acid. That will give me the proper number of 4 hydrogens that are on the product side in addition to that. So it's 2 times 1, that's 2 hydrogens plus the 2 hydrogens that are right there. Perfect. All right, let's move on to problem number 3. Okay, problem number 3 is a combustion reaction, and combustion reactions require a special type of balancing here. So I'm going to highlight problem number 3 because we are going to balance problem number 3 in a particular order. It's going to be first the carbons, then the hydrogens, then the oxygens. You always balance combustion reactions in that particular order. Okay, now you can balance them any order you want to, but I guarantee you this will be the fastest process possible. So how many carbons on the reaction side? 1. How many on the product side? 1. Then check. The carbons are balanced. Hydrogens. 4 hydrogens on the reactant side, 2 on the product side. So I'm going to place a 2 right here, stoichiometric coefficient in front of the water. That will be 2 times 2. That's 4 hydrogens on the product side with the 4 on the reactant side. The next one, we are going to balance the number of oxygens. So we're going to count up the number of oxygens that are right here, and that is 2. We're going to count up the number of oxygens right here. That's 2 times 1, that's 2. There's a plus sign in between them, so that's a total of 4 oxygens on the product side. There are no oxygens in this formula of methane, so there are already 2. So how do I make there 4 on this side? I'm going to place a 2 stoichiometric coefficient right there like that. And now we are done. And now we can check that off. Perfect. By the way, the very last step that you should be doing on every single one of these problems is that you should be checking at the very end if it's correct. If it's correct, then you'll get the correct answer. There is only one correct answer, and that is it. You must have the lowest stoichiometric coefficients possible. So, for example, if we go back to this problem, we cannot have a 2, a 4, a 2, and a 4. I realize that that's the same number of each element on all sides of the reactant and product side. However, it's not the lowest whole number stoichiometric coefficients, and you can divide all these by 2, and then you're back to this answer right there. So you must have the lowest stoichiometric coefficients possible. All right, let's move on to number 4. We have lithium chloride plus fluorine produces lithium fluoride and chlorine gas. There's one lithium on the reactant side, one on the product side. One chlorine on the reactant side, two chlorines on the product side. So I'm going to place a 2 coefficient in front of the lithium chloride. That will give me 2 chlorines on the reactant side where there are 2 on the product side. Now I have 2 lithiums on the reactant side and only 1 on the product side. So I'm going to place a 2 coefficient on the lithium fluoride. That will give me 2 lithiums, but also 2 fluorines. And there are 2 fluorines here on the reactant side as well, and that one is balanced as well. Let's go to the next problem here, number 5. That's hydrogen peroxide decomposes to water and oxygen gas. So there are 2 hydrogens on the reactant side, 2 on the product side. There are 2 oxygens on the reactant side, and 2 plus 1 oxygen. So if I'm going to, if I double this one here, that would give me 4 hydrogens and 4 oxygens. How do I get 4 hydrogens here? I'm going to place a 2 right here. That will also give me 4 oxygens. 2 times 1 plus 2. So that's actually already balanced as well. All right, fantastic. So let's move on. We're going to move this problem on up here just like that, and we're going to go for the next set. So the next set is starting with number 6. Number 6, I have chlorine gas plus sodium iodide produces iodine solid and sodium chloride. There's 2 chlorines on the reactant side, and there is 1 chlorine on the product side. So I'm going to put a stoichiometric coefficient of a 2 in front of the sodium chloride. That is 2 sodiums, and there's 1 sodium. So I'm going to place a 2 stoichiometric coefficient on the reactant side. That will give me 2 iodines, and there are 2 iodines. That one is also now balanced as well. Notice that I can start anywhere I want to on these problems. It doesn't matter. You can just jump right into it. Okay, that was a single displacement reaction. This next reaction, number 7, is also a single displacement reaction as well. We have copper solid plus silver nitrate produces silver and cupric, that's copper Roman numeral 2, nitrate. There's 1 copper on the reactant side, 1 on the product side. There's 1 silver on the reactant side, 1 on the product side. There's 1 nitrogen on the reactant side and 2 nitrogens on the product side. So I'm going to have to put a 2 coefficient right here in front of the silver nitrate. That will be 2 nitrogens on the reactant side and to balance the 2 on the product side. Now there are 6 oxygens on the product side, that's 2 times 3, and there are 6 oxygens on the reactant side, that's 3 times 2. However, now we have unbalanced the silvers of which we had balanced previously. So what we need to do is there's 2 silvers on the reactant side, and now we're going to put a 2 coefficient on this silver to have 2 silvers on the product side. Bingo, perfect. Let's move on to number 8. We have magnesium solid plus oxygen yields magnesium oxide. This is a combination or a synthesis reaction. There's 1 magnesium on the reactant side and 1 on the product side. 2 oxygens on the reactant side, 1 oxygen on the product side. I'm going to put a 2 coefficient in front of the magnesium oxide. I've unbalanced the magnesium, so now I'm going to have to place a 2 coefficient in front of the magnesium element right here. There are 2 magnesiums on both the reactant and product side, 2 oxygens on both the reactant and product side. That one's balanced as well. Let's do number 9. Potassium iodide plus plumbous nitrate produces potassium nitrate and plumbous iodide. Okay, this is a double displacement reaction. And following solubility rules, that's why this is a solid right there. Okay, so one potassium on the reactant side, one on the product side, one iodine on the reactant side, two iodines on the product side. So I'm going to place a 2 in front of the potassium iodide. That will give me two potassiums, and there's one right here. So that will be two potassiums on both reactant and product side now. This will give me two nitrogens on the product side, and there are two nitrogens already on the product side. There's 2 times 3, that's 6 oxygens on the product side, and there's 2 times 3, 6 oxygens on the reactant side. There's one lead, 2 iodines, and 2 potassiums. That one is also balanced as well. Let's move this one a little bit down now, and so we can keep on going with these problems. Perfect. Excellent. All right, this next one is also a combustion reaction for number 10. So I'm going to highlight that here again. We're going to balance it in a particular order. That's carbons, hydrogens, and oxygens in that order, starting at the top, moving down. That is the rule for a combustion reaction. There are 3 carbons here on the reactant side and 1 on the product side. So I want to place a 3 on the product side in front of the carbon dioxide. These are complete combustions. This is propane plus oxygen yields carbon dioxide and water. There are 8 hydrogens on the reactant side and 2 on the product side. So I'm going to place a 4 coefficient on the water. That will give us 8 hydrogens on the product side. Now what we need to do is balance the oxygens. Right here, how many oxygens do I have? 3 times 2, that's 6. How many oxygens do I have here? That's 4 times 1, that's 4. I'm going to add these up. That's a total of 10 oxygens on the product side. I have 2 on the reactant side, and I want there to be 10. So I want to place a 5 coefficient in front of that molecular oxygen, and that will be balanced. Perfect. The next one, problem number 11, is carbonic acid decomposes to carbon dioxide and water. So there's 2 hydrogens on the reactant side, 2 on the product side, 1 carbon on the reactant side, 1 carbon on the product side, 3 oxygens on the reactant side, and 2 plus 1, that's 3 on the product side. Oh my gosh, this one is actually already balanced. An unusual thing, but it is actually already balanced. No problem. Okay, the next one, number 12, that's dinitrogen. That was a decomposition reaction, number 11, by the way. Number 12 is a combination reaction. This is dinitrogen pentoxide. Gas is bubbled into water. This is how you produce acids. Okay, so there are 2 nitrogens on the reactant side, and there's 1 on the product side. So now there are 2 nitrogens on the product side. This is nitric acid. It's one of the 7 strong acids, and is the only one of the 7 strong acids that is an oxidizing acid, so that has special powers, if you will. There are 5 oxygens on the 5 plus 1 oxygen on the reactant side, and then so that's a total of 6. And then there's 2 times 3 oxygens on the product side, that's 6. There are 2 hydrogens on the product side and 2 hydrogens on the reactant side. So that means it's also balanced. All right, let's do number 13, my favorite number, the lucky number 13. And here it is. This is a combustion reaction. Yet again, we're going to balance it carbons, hydrogens, and oxygens, starting with the carbons, then the hydrogens, and finally the oxygens in that order. What we're going to do is we're going to slide this up so that we can take care of this problem here, though. Here we go. Perfect. Just like that. All right. So let's see if we can nail this one down. We have 5 carbons on the reactant side. This is pentane plus oxygen yields carbon dioxide and water. And again, this is a combustion reaction, is actually a complete combustion reaction, if you wanted to be specific. All the reactions that I have here with combustions are complete combustion reactions, no partial combustions, because then you don't get carbon dioxide. You might get carbon monoxide or some other forms. So pentane, there's 5 carbons on the reactant side, and now there are 5 carbons on the product side. There are 12 hydrogens on the reactant side and 2 on the product side. So I want there to be 12, so that would be 6 times 2, that's 12. I'm going to count up the number of oxygens here. That's 5 times 2, that's 10. I'm going to count up the oxygens right here. That's 6 times 1, that's 6. I'm going to add these two numbers up. That gives me 16. There are no oxygens here in this pentane, so that means I'm going to have a stoichiometric coefficient right here in front of the oxygen to balance out the oxygens. There are already 2. I want there to be 16. 8 would be my coefficient. All right, fantastic. One other little note that I forgot to mention, and I want to make sure that this 5 coefficient means that there is 5 carbons and 10 oxygens right here. This 5 does not carry on to the next formula. That's why there's a plus sign in between. Okay, just like this, 8 goes with the oxygen, and that's 8 times 2, that's 16. It doesn't go beyond that or anything like that. Okay, number 14. That is iron plus oxygen gives me ferric oxide or iron 3 oxide. This is a combination reaction. I'm going to start with the most complicated formula that's right here. There are 2 irons on the reactant side and 1 on the, 2 irons on the product side and 1 on the reactant side. I'm going to put 2 irons on the reactant side. There are 3 oxygens on the product side and 2 oxygens on the reactant side. Okay, there's a fractional coefficient way of balancing this, and if you want to learn how to do that, follow my honors chemistry or AP chemistry videos. Really, my honors chemistry videos would cover that. But I'm not going to do that here. What I'm going to do is I'm going to use a different method, and that is the greatest common factor between 3 and 2 is 6. So that means I need 6 oxygens on both sides. How do I get 6 oxygens here? I'm going to place a 3 coefficient here. How do I get 6 oxygens on this side? I'm going to place a 2 coefficient here. And this is why I actually placed a 2 in pencil here in front of the iron, because I knew that I would be rebalancing that. So it's going to be 2 times 2 irons. That would be a 4 right there. So I have 4 irons on the reactant side, 2 times 2, that's 4 irons on the product side, 3 times 2, that's 6 oxygens on the reactant side, and 2 times 3, that's 6 oxygens on the product side, and then that one's balanced. Okay, let's see if I can move this, and then we'll go for the next set. All right, hold on just a moment. All right, so let's keep on going here. Let's do number 15. This is calcium oxide plus nitric acid yields calcium nitrate and water. This is a double displacement reaction, and 1 calcium on the reactant side, 1 on the product side. Let's go for another element. In fact, really what we should be looking at is the most complicated formula, which is this calcium nitrate right here. There's 1 calcium, we just discussed that on both reactant and product side, but there are 2 nitrogens on the product side, and there's 1 on the reactant side. So I'm going to place 2 nitrogens right there like that. All right, now what we're going to do is we're going to look at the number of oxygens. There's 2 times 3, that's 6, plus 1, that's 7 oxygens. 2 times 3, that's 6, plus 7, 1, that's 7 oxygens. There are 2 hydrogens, there are 2 hydrogens. 2 nitrogens, 2 nitrogens, 1 calcium, boom, that one's done. Perfect. So let's scroll this on up just a little bit more and we can do some more problems here. Oh, hey, by the way, a short little bit of advertisement break. Who is this video sponsored by? That is correct. You are correct. It's sponsored by yours truly, the one, the only, the Crazy Hat Chemist. I'm sponsoring this video here today. This next one is sodium chlorate decomposes to oxygen and sodium chloride. So one sodium on the reactant side, one on the product side. One chlorine on the reactant side, one chlorine on the product side. Three oxygens on the reactant side and two on the product side. We've come to something similar to this before, and that is we have a greatest common factor between the 2 and the 3 is 6. So I'm going to place a 3 here and a 2 here. That will now give us 6 oxygens on both sides at 2 times 3 and 3 times 2. But it will also give us 2 sodiums and 2 chlorines, and that's why we're going to have to place a 2 on that sodium chloride. Next one here. This number 17 is a most famous reaction right here. This is the production of ammonia. This is the Fitz-Haber process. So it's a combination reaction with hydrogen, nitrogen. It gives you ammonia gas. And there are, let's see here, 2 hydrogens on the reaction side and 3 on the product side. Lo and behold, greatest common factor, I need 6. So I'm going to place a 2 right here and a 3 right here. That will give us 6 hydrogens on the reactant side and 6 hydrogens on the product side, 2 nitrogens on the product side, and 2 nitrogens on the reactant side. Very famous equation right there, and lots of history behind that. The next one is a decomposition reaction that is mercuric oxide decomposes to mercury, liquid, and oxygen, gas. There's 1 mercury on the reactant side, 1 on the product side, 1 oxygen on the reactant side, 2 on the product side. So I'm going to have to place a 2 right here. That will give my 2 oxygens on the reactant side of the 2 that are on the product side. 2 mercuries on the reactant side, and now 2 mercuries on the product side. I'm going to take one little bit of break right here and making sure that we do not do this. So prior to placing these 2s here, if you were like, oh my gosh, there's 2 oxygens on the product side, well, why can't I just place a 2 here? So this is one of the absolute no's, and that is you cannot change formulas. Placing lower small subscript numbers actually changes the formula. You cannot do that. You can only write the stoichiometric coefficients. Those stoichiometric coefficients are the numbers in front of formulas. That's just how it goes. Now we have the last one right over here. This is a combustion reaction. So I'm going to highlight that in orange again. And how are we going to balance this? First carbons, then hydrogens, then oxygens in that order. That's right. So how many carbons do I have? 6. How many carbons do I have here on the product side? Now 6 with that coefficient of a 6. How many hydrogens? 12. How many hydrogens? 2. So I'm going to place a 6 here to give me 12 hydrogens. Okay, I'm going to count up the number of oxygens right here. That's 6 times 2, that's 12. Plus 6 times 1 oxygen, that would be 6. That's a total of 18. Okay. And I have now this time I have oxygens right here in this formula. So there are 6 plus what number gives me 18? That would be 12. So that means that I need a total of 6 oxygen or 12 oxygens right here. So 12 oxygens would give me that right there. So that's 6 times 2, that is 12 oxygens. Perfect. I think we're done with this. We've done the first worksheet with balancing chemical equations, and I hope that worked out well for you. Make sure you follow along, like and subscribe, and keep on going. Don't stop. This is the real chemistry right here that you're watching. See you next time. Bye for now.